When we try to measure the exact width of a single cell, or the vast distance to a swirling galaxy, standard numbers quickly fail us. Writing out a measurement with 20 zeros is slow and prone to error. That is why mathematicians use exponents, a compression tool to pack long strings of digits into tight, calculable packages. To effectively use this tool, you need to master 3 specific areas: calculating with rational bases like fractions and decimals, applying the laws of exponents to speed up your operations, and formatting your final answers into scientific notation. By the time we finish, you will have the specific mathematical tools required to process distances and sizes that standard notation simply cannot handle. This diagram shows exponents interacting with fractions. When a fraction inside parentheses is raised to a power, the exponent distributes equally. The exponent n applies directly to the numerator a and denominator b. Let's apply this to -2/5 cubed. The cube applies to both the -2 on top and +5 on the bottom. -2 cubed is -8, keeping its negative sign. 5 cubed is 125. Our final answer is -8 over 125. There is a structural trap here. If you write out 1/2 cubed without parentheses, the exponent only applies to the top number. 1 cubed over 2 is just 1/2. You must enclose the entire fraction in parentheses to cube the whole thing and get 1/8. For decimal bases, you have a choice. You can multiply directly, like 0.5 times 0.5, and carefully count your decimal places. Or you can convert the decimal to a fraction first. 0.5 becomes 1/2, and then you apply the exact same distribution rules. You will also encounter negative exponents. A negative exponent dictates that you take the reciprocal of the base. If you have 2/3 to the power of -2, you flip the fraction to 3/2, and the exponent becomes a +2. It does not turn the number itself negative. Applying exponents to rational numbers requires no new math. It only requires strict discipline with parentheses and a careful eye on positive and negative signs. Once you have the core mechanics down, you can speed up the process. The laws of exponents act as mathematical shortcuts, allowing you to bypass repetitive manual arithmetic when calculating large values. This diagram illustrates the product law. Multiplying 2 expressions with identical bases, you simply add the exponents together. The quotient law works in reverse. When dividing identical bases, you subtract the exponent of the denominator from the numerator. For example, 7 to the power of 6 divided by 7 squared. Instead of multiplying out those massive numbers, we subtract 2 from 6. The final, simplified result is 7 to the power of 4. When you have an exponent raised to another exponent, nested inside parentheses, you use the power of a power law. Here, you multiply the 2 nested exponents together to find your simplified base. Then there is the zero exponent law. It states that any non-zero base raised to the power of 0 is exactly equal to 1. Whether the base is 15 or the variable x, if the exponent is 0, the answer is 1. There is a strict constraint to remember. The product and quotient shortcuts fail entirely if the bases you are calculating are not identical. You cannot add the exponents of 2 squared and 3 cubed. By memorizing these 4 rules, you eliminate the heavy lifting. You transform complex multiplication sequences into rule-based logic puzzles, ensuring speed during your exams. Now we return to the extreme physical scales from the beginning of our journey. To express them clearly, we use a universal compression format called scientific notation. This diagram displays the rigid 2-part anatomy of scientific notation. First, the coefficient a. This must be greater than or equal to 1, but strictly less than 10. Second, it is multiplied by a base of 10 raised to an integer exponent. Take the distance from Earth to the Sun, 150 million kilometers. To format this, locate the hidden decimal at the end. Shift it to the left until there is only one non-zero digit to its left. We moved it exactly 8 spaces. Because we moved the decimal 8 places left, our exponent is a +8. The final expression is 1.5 times 10 to the 8th power. Conversely, observe this microscopic mass of a hydrogen atom. To find a valid single-digit coefficient, we shift the decimal 10 places right. Moving right creates a negative exponent, leaving us with 1.67 times 10 to the -10. To keep this straight on your exam, use this mnemonic. L for left means positive, R for right means negative. Scientific notation does not alter the intrinsic value of your number. It simply standardizes the format so you can process extreme measurements without losing track of endless zeros. Look at this checklist. You now possess a complete toolkit for manipulating exponential scales, rational bases, the simplifying laws, and scientific notation. Your primary defenses against common exam errors are purely mechanical. Use parentheses to lock in your bases. Verify those bases match before applying shortcut laws, and you must strictly track your decimal movements. The procedures you've learned today are the exact mathematical syntax that engineers and physicists rely on to calculate distances and masses across different physical scales. You now have the procedures to handle both massive and microscopic values with mechanical precision.
Stick to your checklist, and you are ready for your exam.